Let's say you are asked to design a data structure that follows the constraints of a least recently used cache. A cache is a hardware or a software component that stores the data so that future requests for that data can be served faster. The data stored in the cache might be the result of an earlier computation or a copy of data stored elsewhere. Now, these high-speed memory are often smaller than your secondary memory. Therefore, we have to be really picky about what kind of data we are removing or adding. And this is where the page replacement algorithms comes into picture. An operating system that uses paging for virtual memory management, page replacement algorithm decides which memory pages to page out, or sometimes called that swap out, or write to memory when a page of memory needs to be allocated. Now, these two things out of the way, before jumping into how LRU actually works, we have to understand two terminologies, which is page fault and page hit. Now, page fault in simple terms means that the data that we are trying to look for is not there in the cache. So we can say that the data that we are trying to look for is absent. In that case, it will be a page fault. Whereas by now you must have guessed it that page hit means the opposite, that the data that we are trying to look for is already there in the cache. So we'll say present. Okay, so now that we know about these two terminologies, let's take a look at how LRU actually works. Okay, so let's see how LRU cache actually works. We are given with a cache of maximum capacity 2, and initially this cache is empty, and the maximum capacity will always be a positive number. Along with this cache, we are given few queries, and you can see that out of all of these queries are either a put query or a get query. The put query is provided with two values, which is basically a key value pair, and a get query is always given with a key, and we have to return its corresponding value. So let's start with the execution. So first we have a put query. Since our cache is empty, so we can definitely add this value. So this is what our cache will now looks like, and the capacity is now incremented by 1, which means that we have added a value to our cache. Again, we have a similar query but a different value, which is 2,2. So now we'll add this. So since the capacity is not the maximum capacity, we have space. So we can say 1,1 and 2,2. Now, one more thing that we have to make sure is that we have to make this 1,1 the least recently used data, whereas 2,2 will be the most recently used data. Now, the third query is get 1, which basically means that we are trying to get the corresponding value with key 1. So this will simply return 1. Okay, and at the same time we have to make 1,1 the most recently used element, and 2,2 the least recently used element. Okay, after that we see that we have a query of put 3,3. Now this is the interesting part. So since our capacity is now 2, we can't include a new data, okay, without removing some data which is already there. So now how we can pick that which data we should remove, right? So since the algorithm, the name itself is least recently used, so we'll obviously remove the least recently used value, which is 2 in this case, since we just now, before this query, we just now try to get this value, which makes it the most recently used element. So now this is what the cache will look like. So we have 1,1 and 3,3, and now 3 is the most recently used and 1,1 is the least recently used. Again, the capacity will remain same, which is 2. Again, we have get 2, which means that since we don't have any key 2, and we don't have any corresponding value either, So we have to return -1, which basically means that the value is not found. Okay, so we will say return -1 in this case. Again, we have a value of put 4,4. Now think about it. If you go back in the history of our query execution, we'll see that the most recently executed query was put 3,3, which means that we added 3,3. So automatically 1,1 becomes the least recently used element, right? So we have to remove that, and 4,4 will take place of 1,1, and this is what our cache will look like. Again, the capacity is 2. Okay, so again the query is get 1, which means that we have to look for a key 1 and its corresponding value. Since we don't have any key, so we have to return 1 in this case. Again, we have a get query of 3. We have 3, so we'll return, we'll find the key and its corresponding value is 3, so we'll return 3. But the interesting part is that since we have a query which involves 3, so this becomes the most recently used element and most recently used data or element, whatever you want to call it, and this makes the 4,4 least recently used. So let me just write it here real quick. We have LRU as 4,4, but if we see the 9th query, which is get 4, we will return 4 in this case, since we will find that okay, 4 is there and the corresponding value to the key of 4 is 4, so we'll return 4. But now in this case we have LRU cache as 3,3, because since we just now tried to query 4,4, so this makes 4,4 as the most recently used element and 3,3 as the least recently used element. Now while explaining this example, I observed few things. So let's see if you were able to catch these or not. So here are my few observations from the example that we just executed. The first observation is that the query are either a get query or a put query. Or let me just write it in cap, get or put. Okay. The second one is that if whenever the query is a get query, so let me just write it like this. Whenever the query is get query, we are essentially doing two things. Okay. The first thing is that we are making sure that if the data is already there or not. If it's not there, we return -1, if you remember. So let's write if the data is not found, okay, we return -1 in that case. And the second thing that we do is that, okay, let's say the data is there. So in that case, we make that data the most recently used data, right? So else we make that data the most recently used data. Okay. And in case of the put query, there were 3 things that we were doing. Let's see. So the first thing was that we were checking if it already exists or not, and if yes, then we make it the most recently used element. So same whatever I have written here. So let me just write it real quick. If key already there, just make it most recently used. All right. Apart from that, if the data doesn't exist, which means that if it's a new data that we have to add, okay, so but not so quick, because we have to first check that if we have reached the capacity or not. Okay, so I'll write something like this. So let's check the cap, or basically the capacity of cache. Okay, now if we check, so we have like two options. So if like the control flow will go either to this or to this. So if the capacity of cache has been reached, in that case we'll remove the LRU least recently used data and add the new one in place of that. Okay, so let's write it in short form. So let's say we'll perform LRU, or let me write like this: remove LRU and add the new element. And also it goes without saying that this new element will be the most recently used element, right? And in case if the data this case will be executed, this scenario this case is executed in a scenario where the capacity of the cache is reached. In case if it's not reached, then I think we are safe to add that data to the cache. Okay, so we can say that we can add that data safely. Okay, now that we are clear with the algorithm, let's think about the data structure. So essentially what we discussed here is the algorithm of whatever we have done in this in the previous execution of the example. So now that we are clear with the algorithm, let's think about the data structure that we can use to implement this algorithm. Okay, now unfortunately we don't have a single data structure that have constant time lookups, constant time insert delete, as well as maintains the order. Okay, but we have two different data structures that can be useful, which is hash maps and doubly linked list. Okay, so let's code this out and we'll see how we can use these data structures. Okay, let's start with the most interesting part, which is coding out our logic. And before we get started, huge shout out to Fentowell, who is a LeetCode user. I saw his solution in the discussion forum and I found it really good, so I thought why not use it in my example. So yeah, so let's start by declaring all our variables and the data structure that we'll be using throughout our program. So we have the capacity, we'll call it m capacity. Then we have list of pair. Okay, and this pair is basically key value pair. Let's call it m list. Also we'll have a unordered map which will help us with the constant time lookup. Unordered map, and this unordered map will take n type as its key, and the value will be the address of that a pair which is there in this list, m list. So we'll do something like iterator. Cool. Let's name this list m map. Okay, so I think we are done with declaring of all our variables and data structures. Let's try to initialize the capacity variable in this constructor. We'll do something like m capacity with capacity. Okay, also I think so this part is done. Let's complete this get function. So if you remember the algorithm that we discussed a couple of minutes ago, that before returning any element, we have to first check that if that element is already there in the hash map or not. So we'll do the same. We'll do auto found iter is equal to map dot find key, and if we found, or I think let's do it other way around, if the found iter is equal to m map dot end, in that case we have to return -1. Okay, and if it's already there in the hash map, then we have to make sure that we make it the most recently used element. Okay, now how we can make it the most recently used element? By simply moving that node to the beginning of the doubly linked list, or the list that we have, m list. Okay, so we can use this really cool STL this function in STL library called splice. And what we can do is we can pass the beginning of the list where we want to add that element, also the list from which we have to take that element, also the reference to that element which will be there in the found header at this second position. Yeah, that's right. And once that's done, so basically we have moved that element to the front of our list, making it the most recently used. We have to just simply return the value to the corresponding key. Okay, so how we can do that? We can do something like found header second. Cool. So let's quickly revise what we have done so far. So first we try to get the position of where this key is in our hash table. If it's not there, then it will obviously point to null. So in that case we will return -1. In case if it's there, then we have to make sure that we move that node to the front or the beginning of our list, and we use this amazing splice function to perform this operation. And once this is done, we simply return this value, which is the value corresponding to this key, okay, that is passed already in this function. So yeah, I think we are good to go for the get function. Let's try to complete this put function. Okay, so for put function, I think first we have to again check that whether the element is already there in the hash map or not. So for that we'll use the similar logic as we used here. So let me just I think we can save some time by just copy pasting it. And once that there, I think we can do if found header is now in this case we'll see that if it's not equal to mmap.end, which means that element exists, and if the element exists we have to make it the most recently used element, and at the same time we have to update that value. Because think about it, in a case where first we added that element with a key 1 and value, let's say 30, okay, and second time we call the same function, but this time we have updated the value. So let's say the updated value is 70. So in that case we also have to make sure that we update this value. So we'll do something like mlist dot splice and basically this whole function. Okay, yep. And once this is done, so we are moving that node to the beginning of the list. Once that is done, we just simply update the value. Perfect. And once this is done, we simply we simply return. In case if the value is not there in the hash map already, we have to add that element. Now before adding that element, we have to obviously make sure that we if we are out of capacity or not. Okay, so we'll do something like mmap.size is equal to capacity. If yes, then we have to remove the least recently used element and then add on the new element. Okay, and and on the other hand, if let's say the capacity is not reached, in that case we can just simply add the element, right, because we have enough space. So we can do something like int key to delete is equal to mlist dot I think we can do back dot first. That way we are just getting the key which we have to remove. So we do something like mlist dot pop back, and this is the advantage that we get by using a doubly linked list, that we can easily pop back. Also we have erase mmap dot erase, and we'll erase by the key that we just found, the key to div. Perfect. Once this is done, so basically these three lines, or basically this these three lines were done to remove the least recently used element. Once that is done, we can simply add that element. So we can do something like in place front, in place front, and we'll pass on key value which creates a node and add it to the front of the list or beginning of the list. And also we have to make sure that we update the hash map as well. Okay, so we do something like mlist dot begin. Why begin? Because we just executed this line of code which guarantees that the new element is the most recently used element and is at the beginning of the list. Okay, so I hope everything's working fine. Let's try to run this, see if anything went wrong. Okay, looks like in place font. Okay, I made a small typo. It should be front. What else? Okay, perfect. So I think the sample test case is running fine. Let's submit this question. Perfect. So it's running fine. I hope the logic is clear. We moved step by step. If you have any doubt, feel free to ask in the comment section down below. Till then, peace.